All right, so we are now recording. All right, so it's my pleasure to introduce Elchanan Solomon, who is now a fancy Philip Griffiths assistant research professor at Duke University, basically super postdoc. And we're very happy to have him give the second talk of the ATiA seminar this semester. And I will let you take over.
Thank you very much. So the title of the talk is, as you can see, Geometry to Topology, Inverse Theorems for Distributed Persistence. So this is joint work with Alex Wagner and Paul Bendich, who's with us today. So please feel free at any point in time to interrupt me with any questions or concerns you have. Okay, so the intro slide, so in which I'm going to make my argument why the traditional invariant used to sort of measure the topology of large point clouds isn't very good. So I claim that the full persistence diagram of a large point cloud is, first of all, very expensive to compute. This is the cheesiest of the slides that I have. Unstable to outliers, by which I mean that it's stable in the sense that if you move each point a little bit, the persistence stays roughly the same. But if I have that torus point cloud and I add a point far away, or I add a point in the middle of the torus, the invariant will really change completely. And the last one is that it's far from injective. In other words, that two different point clouds could have completely different, two different point clouds could have exactly the same persistence diagram, or at the very least, they could have very similar ones. Now, when I was discussing making these slides with Alex Wagner, he said, the Pokemon example isn't actually such a bad failure of injectivity, but the persistence example is much worse. So take that for granted. Okay, so our setup is going to be the following. So we're going to let lambda be some invariant of point clouds, generally a topological invariant, although this definition doesn't require it to be topological. And x, some abstract set, which I'm embedding into Euclidean space. And I'm going to define the following distributed invariant. So I have some size parameter k. And the invariant is, I'm going to keep track for every subset of S of x of size k, the invariant that I get on that subset. After I've embedded in Euclidean space. Actually, I think this is an important point which isn't mentioned in the archive version, but I'll put up everything that I say in this talk with the word rips attached to it works in any target metric space like a manifold, and anything with the word check attached to it doesn't make any sense anyhow, so you don't have to worry about that. But this works in much greater generality than Euclidean space. Okay, so we'll call this distributed persistence, or just a distributed invariant. So this is very fast to sample from and parallelizable. In the sense that if we're working with an invariant that's very quick to compute for small sets, such as persistence, it has the standard persistence stability because it's really just lots of persistence calculations, but it's also more stable to outliers. So you can imagine a situation in which I had that torus and I put a point somewhere in the middle. Most subsets that I sample are not going to see that point, so their persistence isn't going to change. So things only change when I pick up a subset containing an outlier. So in that case, it's more stable to outliers. So the question is it any good? Does it have a lot of data? How does that data depend on the size of the subset that I take? And what if we only have access to a small sample of those subsets? Because there's a huge number of subsets of a fixed size. You're never going to compute, the persistence of all of them. But what if you just compute the persistence of, 100,000 of them or 10,000 of them? Okay, so let me be clear about what invariants I'm thinking about. Rips persistence, check persistence, rips Euler curves, and check Euler curves. Another thing I want to make clear, this is both for theoretical and computational purposes, is we don't often, or at least I don't often compute the full persistence of the full filtration. You often work with a skeleton. Computationally, things become really terrible when you work with a sort of high dimensional skeleton. So we're also going to allow ourselves to restrict to a M skeleton, and I'm going to call that lambda superscript M. Okay, so let me give you a small case study to motivate this. So I have three point clouds. One of them is sampled from a circle, one sampled from a disk, and one I sampled mostly from a circle and a little bit from a disk, which we'll call the noisy circle. Okay, so let's compute their three persistence diagrams. So the circle is in red, shouldn't be too surprising. The noisy circle is in green, and the disk is in blue. So from this persistence diagram, it looks, it looks like the noisy circle looks a bit closer to the disk than the circle. And in particular, you couldn't really detect from this persistence diagram that the noisy circle has a big circle sitting there, which is, important information. But what I can also do is compute a bunch of persistence diagrams of subsets of small size, like subsets of size 10, compute their persistence images, and for the purposes of visualization, let's just average them. So that gives me these sort of three distributions. The blue is for the disk, the red, I try to have consistency here between my figures, is the circle, and the green is the noisy circle. So here actually you see, so you might see where's the red? Actually, the green and the yellow, the green and the red have significant overlap, and as you may remember from primary school, that creates yellow. So a lot of the time they actually give you the same persistence diagram, which is what you'd expect, but you also see that somehow this green region interpolating between the red and the blue, and that tells you that sometimes you also get some contractible stuff, which is, I think, a pretty good story. Now, taking the average of all these diagrams is very destructive. It gets rid of a lot of information, and we could talk about at the end what else you can do, and that's an interesting question we're thinking about. But even just taking the average is enough to tell a very important story that the persistence diagram doesn't see, and it is extremely fast to calculate. Okay, so now let's get to some theory. So let's talk about some limit cases for the size of the subsets I'm interested in. If I only look at subsets of size 2, and I compute their persistence diagrams or Euler curves or whatever, the real only information there is the distance between them. So that's purely geometric information. On the other hand, if I look at the size, which is the size of the whole space, I just get the full persistence diagram. So that's topological information, or let's say topological metric, because there's some metric information also in persistence diagrams. So the question is, what happens to intermediate values of K? So from this, we see if you know all subsets of size 2, you know all the pairs of distances, that actually determines the whole isometry type of the point cloud. So what happens at K equals 3? Already at K equals 3, this fails. There's a pretty common example in sort of inverse theory of persistence. If you take a bunch of points sampled from like two intervals glued together at an angle, as long as the angle is obtuse, you really can't tell what angle it is. The persistence diagrams are always the same. So I guess what information can you figure out then? Already at K equals 3, you can't determine all of the geometry. So here's what you can say. So for simplicity, I'll assume M is equal to 1. So we're only working with one skeleton at the moment. And then I'll tell you what happens in general. So let's take K equals 50 as just an example. Let's suppose I knew the persistence diagrams of all subsets of size 50. What could I deduce from that? Actually, I have no idea. That's a great question. We could talk about that later. But if I knew all subsets of size 50, 49, and 48, that taken together determines the geometry of X. Now you might ask, what's special about 50? There's nothing special about 50. It just has to be any 3 in a row. Why 3 in a row? Why not 4? Actually, that's connected with M. If M was equal to 2, it would be 4 in a row. If M was 3, it would be 5 in a row. I'll explain the logic of that in the upcoming slides. But here's the injectivity theorem. For any of the 4 invariants that we're looking at, and the M skeleton invariant, if I know, and for any K, so K could be 50 or 100, if I know K, K minus 1 up to K minus M minus 1, which is like M plus 2 in a row, I can determine the information of subsets of size 2. And we know that subsets of size 2, that's just geometric information. From that, I can determine the isometry type. So I'll get to question.
Yeah, sorry. I just wanted to make sure I'm understanding. So when you're looking at lambda 1, for example, should I have in mind something like persistent homology in degree 1? The reason I'm a little confused is because, obviously that depends on 2 skeleton information. So I just want to make sure.
Oh, right. So it's I'm actually taking, for the persistence diagrams, all the
degrees of homology.
All the degrees of homology.
Okay. All right. So it's kind of almost like a persistent homology transform type thing. Where
yes.
You stack all the degrees at once.
Yes. But to make the proof work, you have to like throw everything and just use Euler curves anyhow. But
yes.
But to build the Euler curves, you need all that information. So exactly.
Okay. So when you say using the M skeleton invariant, oops, looks like Uli got kicked out and is coming back in. So when you're saying using the M skeleton invariant, you mean that you only just use the M skeleton of your say RIPS construction or whatever you're doing.
Yeah, I when building the RIPS complex, I never insert anything higher than an M cell.
Okay. All right. Cool. But we're keeping in mind via torus RIPS check persistence and things like that, right?
Yeah.
All right. Cool. All right. Thank you.
Okay. So now, injectivity, that's pretty good, but actually we can go much farther than injectivity. So let me introduce 2 pieces of notation. The first thing is what we mean by a quasi-isometry. There's like many definitions of what a quasi-isometry is, but let's say the quasi-isometry is a map between 2 metric spaces such that distances in one and distances in the other never differ by more than epsilon. So this so this is our definition of an epsilon quasi-isometry. Maybe you have a different name for it, so then substitute that for it in the talk. There's another thing that just shows up in the proof. It's just the sum of the following binomial coefficients. It just shows up in the statement as a constant. So if you see the constant, you wonder, what's that constant? It's this. It turns out Wikipedia told me it doesn't have a closed form solution. So that's why we give it a name. Okay, so now here's the big inverse result. So to talk about stability, I need to be talking about an invariance that has some geometry to it. So I'm going to be working with the persistence invariance. So let lambda be either RIPS persistence or check persistence. And let's suppose I have a bijection between 2 spaces such that for all subsets of size k, k-1 through k-m-1, so k could be anything. So it could be, if m is equal to 1, it could be 50, 49, 48. So it's just some collection of sequential sizes. I know that the bottleneck distance between the persistence diagrams in X and the associated subset in Y are within epsilon. So notice, by the way, so if epsilon equals to 0, that just says that all the persistence diagrams are the same. But now we're allowing for the possibility that it's greater than 0, but this doesn't have to be infinitesimal. This is any epsilon. Then it turns out that, so if the invariant I used was RIP persistence, this is a quasi-isometry where the quasi-isometry constant is quadratic in the size of the subsets, the sort of largest size k. And if it's the check persistence, so it's this other, basically, it's a higher degree thing. I mean, in practice, we don't really ever use more than like MBM is equal to 2, in which case it's like cubic or quartic. But so that's essentially the scaling. So notice when epsilon is equals to 0, this just says that the 2 spaces are isometric. That's the injectivity theorem. This says if all the invariants are close, then the spaces must be close. In fact, that map is a quasi-isometry. Now, you might be wondering, RIPS and check information aren't that far apart from each other. There's somehow this interleaving. So yes, if you're in Euclidean space, you can improve the bound in the check case to quadratic as well. Because you know that if the check persistences are close, then the RIPS persistences are also kind of close. So this works in general if you're working with Euclidean point clouds. If it's not a Euclidean point cloud, well, maybe there's no check persistence, so it's okay. So the takeaway here is there's quadratic interpolation between geometry and topology. When k is equal to 2, you're just looking at collections of subsets. That's really just the quasi-isometry distance between the spaces. As K gets bigger and bigger, the subsets gets larger and larger. It's more and more topological information. And as you hit K equals the size of X, it's just measuring the distance between the persistence diagrams of X and Y.
So I have a question. I just want to make sure I'm following. And so I'm just a little confused about the statement of the theorem. So we have a bijection of point clouds, but possibly equipped with different metrics, correct?
Well, yeah, the metric is always in this. Let's say for right now, everything is in an ambient Euclidean metric.
Okay, all right. So I've got some map of point clouds that's bijective, and then I'm asking furthermore that for any size K subset S, or I guess where K S lies in this parameter region here, that then the bottleneck distance between that set S and let's say the image of S under phi being less than epsilon. And then under the assumption that the invariant you're looking at is, let's say, Rip's persistence, then you can deduce that phi is a bilipschitz map with that particular constant, or whatever we're calling our quasi-isometry here. Is that right?
Yes, exactly. The map phi, which we only knew to preserve topology up to for some subsets up to some bound, is actually a geometry preserving map. Yeah, and the constant is quadratic in K.
Oh, okay. So just to say it back one more time. So the fact that we've got this M skeleton invariant lambda, and that we can test this sort of distortion on these size K through K minus n minus 1 size subsets, then we can deduce globally that this map phi had to be essentially this quasi-isometry, right?
Yeah.
All right, cool. All right, so now
I have a question too.
Please.
Do you expect there to be like any kind of converse to this statement?
In other words, if the spaces are close in quasi-isometry, then the invariants are close?
Yes.
So that's standard, that's persistent stability. So then it's actually going to be one Lipschitz.
Right. Gotcha. Thanks.
Okay, sure. So let's continue. Okay, so let me go through the proofs of these statements. Let me start with the proof of the of invertibility, the injectivity result, which will be leveraged to prove the result I just showed you on the last slide. Okay, here's a question. Do lambda, so if I know, let's suppress for the moment, let's assume that m is equal to 1 for the moment. Again, I'll explain what happens for larger skeleton. Do the subset, knowing the topology of subsets of size K and K minus 1, allow me to move one step down? So here's an example. Let's suppose I knew the, okay, so let me just say something ahead of time. I'm now only going to work with the Euler curve invariant because the persistence invariants have strictly more information. So let's suppose I knew the Euler characteristic at every parameter value for all subsets of size 5 and 4. That's what the Euler curve information has. What can I say about subsets of size 3? So let's take an arbitrary subset of size 3 here, Y. And I'm going to build two three other spaces. So Y1, Y2, each of which has an extra point attached. And then W, which is the union of them, which is 5 points. Now, W is the union of Y1 and Y2, and the intersection of Y1 and Y2 is the space Y. Now, the inclusion-exclusion formula for the Euler characteristic at any given parameter value R should relate the Euler characteristic of the space Y to the Euler characteristics of Y1, Y2, and W. So if you knew those, you would do a little inclusion-exclusion kind of argument. Now, that almost works, but the union of complexes is not the complex in the union. In particular, look at that red dashed line in W. That edge is not contained in either Y1 or Y2. So even though W is the union of Y1 and Y2 as sets, it is not, you cannot say that for the complexes. So no, that's not correct. But if you have 3 in a row, it does work. And why does it work? It works because, well, I can cover this W by Y1, Y2, and Y3. So I make sure that I have all the edges. And then if you use the inclusion exclusion argument, you have to, more terms pop out. You have to look at all the pairwise intersections and the triple intersections. But now everything here is kosher. Everything is really, you can really use inclusion exclusion, and you can deduce the other characteristic of Y in terms of all the W, Y1, Y2, Y3, and all the intermediate pairwise intersections. So that tells you if you have 3 in a row, how to go down 1. Now that's only for m equals 1. What happens if it's m equals 2 is so you're missing a triangle? Well, you have to use, instead of Y1, Y2, and Y3, you also have to use a Y4. And therefore, when you look at all the possible intersection spaces that show up in the inclusion exclusion argument, you see you have to go back, you have to go 1 degree lower. So that's basically why the dependence on M shows up. Okay, so assuming you followed that, so how do we deduce the theorem? So if I know 50, 49, and 48, I therefore know 47. But if I know 49, 48, 47, I know 46. And then I repeat that until I know 2. But I've told you that subsets of size 2, it's just geometry. So that's how the proof works. Okay, so let's move on from this, and let's see how can I use this to solve the more challenging question of invertibility when the persistence diagrams are just close instead of being exactly the same. Okay, so here's what I'm going to do. So we have our invariant, either rips or check filtrations, and we know that for the subsets of X and Y, the persistence diagrams are not exactly the same. They're almost the same. They're within epsilon of each other. We're going to cook up a new filtration that makes all the persistence diagrams exactly the same. And once they're exactly the same, we can use this inclusion exclusion trick. So you might be wondering, what filtration are we going to cook up that makes everything exactly the same? We're just going to round the filtration to a discrete set of values. So here's an example. Suppose I have this curve. Here's its persistence diagram visual, I guess barcode visualized, where the sort of starting at local min and terminating at a local max. And I'm going to impose a grid on it. And so if I impose a grid and I round the critical values, or just, to the grid, I get this. So I could look at its persistence diagram or barcode, and I can compare it with the original. You see that bars which were almost the same have now become exactly the same. Okay, so we claim, this requires some technical arguments that I'm going to explain soon. We claim that there is a filtration I can do that makes all the diagrams of interest that were close actually become equal. So there's a little technical lemma, and which has nothing to do with persistence diagrams, and it goes as follows. Let's suppose I have 2 sets of points, P and Q, and every point in P has its pair in Q. So every PI has its pair QI. And so I can compute for each pair the distance between them. So that's DI. And then I can look at the maximum of the DI and their sum. You'll see from the proof why the sum shows up. So my claim is there is some subset that I could round, some subset of the real line that I can round to. In other words, I round every element to every element on the real line to its closest element in R, such that every point in P and its associated pair in Q have to get rounded to the same place. So that forces the persistence diagrams to collide. But another thing which is really important is we know from persistence theory, if you don't adjust the filtration too much, you don't adjust the invariance too much. So the second property is nothing gets moved too far. Nothing gets moved more than 3 epsilon plus 4 delta. In particular, since epsilon is less than delta, we can just replace that with 7 delta. So I'm going to show you how the proof works. And the proof is a little technical, but I made an animation that should give you the flavor of the proof. So it's a little cheesy, but I hope it explains something. So the points in black will be P, and the points in magenta maybe will be Q. Okay, so here's all the points P and Q. I am going to build the set R that I'm going to round to. And in order to have sort of nearby points round to the same thing, I want the points in R to be somehow spaced far apart from each other. So let's take this to be the first point in R. So far, so good. Now let's propose that this is the next point in R. Does it seem like a good idea? Well, let's look at the midpoint between this point and the last point. You'll see actually that there's a couple that got split up. One is on the left of the midpoint, one is on the right. So we want to reunite this couple to make the lemma true. So we're going to move this a little bit to the right. And that moves this a little bit to the right. And in fact, you only have to move to the right, basically proportional to the distance between the couple. Okay, so that's all good, but now there's another couple that's been broken up. Well, okay, we can move a little bit to the right again, and we could save that relationship. And then now we're over here. And as we keep on doing this, we pick up copies of DI for all the couples that we had to reunite. So that's how the sum shows up. And okay, right now all the couples are good, so we'll put a point there. And that's the next point in R. Okay, then we continue along our way. Oops, I can't actually see. So yeah, so now we pick the next point and we repeat the argument. So that's somehow where this delta shows up. You have to somehow move the point that you pick to the right to reunite the couples. And you never have to reunite any couple more than once. So that's how the sum shows up. Okay, so now let's get to the proof of the main theorem. Take an arbitrary pair of points in X. Find a set of size k containing them. I'm now going to look at all the sets, all the appearance times of simplices in S. These are essentially going to be the birth times and death times of, in persistence diagrams. For the ribs, this is about k squared. For check, it grows with m. Actually, it's that S of km thing earlier. So now here is I'm going to use the rounding lemma. I'm going to try to make sure that every appearance time gets rounded to that value plus 2 epsilon and that value minus 2 epsilon. So if you look at the figure in the top right corner, so if there's a point P, I want to make sure that P gets rounded to the same place as those 4 points, A B plus 2 epsilon, A B minus 2 epsilon, A plus 2 epsilon B, A minus 2 epsilon B. And naturally, everything in the green square also has to get rounded to the same place as well. But what this does is it actually forces that once I work with a rounded invariant, all the persistence diagrams for subsets of S and subsets of phi of S have to be exactly the same. Because I assumed that everything was within epsilon to begin with. You might be wondering, why is there a 2 epsilon there? The 2 epsilon just basically has to work with what happens if stuff gets rounded to the diagonal. That's why there's a little, otherwise it just adds an annoying factor of 2. That's why there's like 112 and all these, yeah. 2 divides the final constant many times. Okay. So now we apply the inclusion exclusion trick to the rounded invariant, and we therefore know that whatever the value of the rounded invariant is on a subset of size 2 in S, in particular on x1, x2, it has to be the same thing on the pair of points 5x1, 5x2. Here's where we use persistence stability. The rounded invariant and the original invariant use filtrations that are very close to each other because the way I defined the rounding, nothing got moved too far apart. So actually, the triangle inequality tells me that lambda x1, x2, the original invariant, and the original invariant associated to 5x1, 5x2 are close. And that's just the distances between them. And that just tells us that those points, that gives us the bound on the quasi-isometry distance. So that's the proof of the main theorem. So I'll pause for a second if anybody wants to ask questions.
Yeah, I might just ask, this is all directed at proving invertibility of this distributed persistence invariant, is that right?
So this proves the inverse by Lipschitz.
The inverse by Lipschitz. Okay, so so getting at this claim that if you have all these sort of size k invariants and tested on size subsets of size k, then then you can deduce this global bilipschitz property.
Yeah.
And somehow rounding off the filtration values that you see in both when you're filtering internal to X and then when you're filtering internal to Y, this sort of is the thing that makes this work, right?
Yeah, so to go down from k minus 1 all the way down to 2, we have this inclusion exclusion trick.
Yes.
But you have to know that it works the same way in X and Y, and it won't if their persistence diagrams are different.
So you have to put them on common footing.
Exactly. I forced them to be the same. And then I worked down to subsets of size 2. And then I said, actually, this new invariant and the old invariant weren't that different to begin with because I never moved anything too much. So then I get this quasi-isometry band.
Can I ask a question? This should be real simple. I suppose you can relax this condition on phi being a bijection by allowing an image that's dense enough and perhaps point inverses that are metrically small?
I'm not quite sure when you mean by relaxing the bijection. So are you suggesting not to start with the bijection?
Yeah, just instead of bijection, just require that phi has a dense enough image, and perhaps for injectivity, something like the inverse image of each point is small, has a small diameter.
So if you want, so one thing I can say, if you want to replace, if you want to just work with like dense subsets of X and Y, and there's a result in the paper to this effect, and it replaces the quasi-isometry distance with the Gromov-Hausdorff distance. But if you want to get rid of the fact that the map is a bijection, I would just have to think about whether or not something is there's any technical point that gets messed up. So that's a great question. I'd have to think about it, but I will talk a little bit about simplifications that you can make to this construction.
All right, thanks.
Cool. And Elchanan, just so you know, we started 10 minutes late and we usually go for about an hour. So you still have about, I would say half an hour. So no rush.
Okay, thank you. So let me talk about some practical concerns.
Can I just make a comment quickly? Sorry to interrupt.
Yeah.
Yeah. Well, returning to Washington's point from a moment ago, you mentioned at the beginning of the talk that not only is this construction stable, but it also has some kind of robustness property. I believe you haven't mentioned what that robustness property is yet, but Washington's question sounds to me very much like a request for kind of like an inverse robustness property. So I wonder if you can speak to, maybe you'll tell us more about robustness.
What do you mean by inverse robustness?
Well, I don't know exactly, but.
So,
I mean, if you have a bijection with like just one extra point added in the codomain, like you're a bijection up to cardinality 1, then that's like a small perturbation of your bijection situation, and you would hope that you would still be able to recover a similar result. So I think a statement like that would be some kind of special case of inverse robustness. I don't know how to make it more precise.
Yeah, I have to think about it. I mean, so intuitively, I think if the sets have different size, you can always just like double one of the points in the other one. And so I guess I have a bit of talk brain right now. My intuition is that I think I won't take the full hour, so we can discuss it. My intuition is a lot of things can be relaxed here. That I haven't necessarily thought to relax, and I'd like to discuss it. So that's not an answer, that's an invitation for more conversation, but I hope it will work. So let me talk about some practical concerns, not the concerns that ended up concerning you. So first thing is, this doesn't actually require checking all subsets of a specified size. If you actually look at the proof, you need very few subsets to make the proof work. You basically just need enough subsets to cover all pairs of points of size 2. So it ends up being roughly quadratic. If you pick subsets randomly, so pick subsets randomly means you just sort of pick without replacement of a fixed size. So I don't mean completely randomly here. There's a slight caveat in the construction. It turns out that, so the first thing is, so I said the injectivity results don't require checking all subsets of a specified size. So you might tell me, oh, maybe there's some very special collection of subsets that works. Actually, there's nothing very special about it. Even a random collection, under certain conditions does the job. You don't have to be very choosy about how you pick these subsets. You can check even fewer subsets if you want to relax quasi-isometry to Gromov-Hausdorff. You can check even fewer subsets and actually get a linear in K bound if, in addition to requiring that phi preserves topology, you also ask it to preserve some sparse set of edge lengths in advance. So a little bit of geometry. I don't think that's ad hoc as it may sound. There are some examples, some applications in mind where that might be feasible. That's future projects, but all these extra details are in the paper, and I can discuss them later. I have extra slides after the ending slide in case people have questions. Okay, so let me talk about some cool simulations. So I'll start with a circle and move on to a torus. So suppose X is a circle embedded in the plane, and I'm going to let Y be the same circle where I've added a lot of noise. And there's a bijection between them, just sending every point to where it ended up. There's sort of a continuous color gradient to kind of tell you which points were supposed to be near which. So now we can try to fix Y to get its topology to be closer to X. So how do we do that? Let's randomly pick a subset of size. In this case, we use subsets of size 25. So K equals 25 of X. And we looked at the corresponding subset of Y. We compute their two persistence diagrams. And then, I think it's well known that a lot of these persistence losses are differentiable. We can actually adjust those 25 points in Y to bring their persistence diagram a little bit closer to the persistence diagram of the correct points in X. And we can keep on running that each time, randomly picking points. And you can do gradient descent. And if you wanted to converge a bit faster, you use some momentum. And anyhow, what you see is that the circle kind of reassembles itself. So all we did was try to fix the topology of subsets of size 25. But what it ended up doing is kind of reconstructing the circle largely. And we could do the same thing with the torus, and that's in the bottom. So X, we start with the torus, and then Y is just the torus with a lot of noise. And you do the same thing. You randomly pick subsets, and you try to move the subsets in Y in the messy space to bring their persistence diagrams a little bit closer to what the true persistence diagram is in the reference space X. And it turns out that this actually does a better job than the circle. It really reconstructs the torus. So this says something in addition. This says in addition to the theoretical results. So so the theoretical result says that if you can fix the topology, you can also fix the geometry. But it isn't necessarily clear that you can always fix the topology to begin with, especially starting with such a large amount of noise. And this example says, actually, sometimes you can. And more experiments are needed to confirm that. Let me talk about some applications of this. How would you use this invariant? So one example is topology preserving dimensionality reduction. So I want to map a point cloud to a low dimensional space. And my loss is, I want the projection to preserve the topology of random small subsets. We know this is actually something differentiable, so you can optimize this. Shape registration. This is an interesting question that I'm thinking about how to do this, but you can try to think of, suppose I give you two shapes, which I know there should be some like quasi-isometric map between them. You can try to find such a map by making sure that it preserves the topology of random small subsets. And then the theory says that will actually globally give you a good quasi-isometry. Another example, I think this is probably the most promising, just feature extraction. Use the collection of persistence diagrams that you get as a feature. It's very quick to compute. Let me talk about some open problems. That's some projects that we're thinking about. Okay, so to make all the theorems work and to do this inclusion-exclusion argument, our invariants are labeled. So we remember which invariant came from which subset. In practice, especially if you're going to be using it as like a feature in a machine learning pipeline, you're not going to use the labeling. So this is kind of similar to the persistent homology transform, where I throw away the information about which sphere direction it came from. So if you throw away that information, things become more difficult. So what inverse results can we have in this setting? I don't know. You have to really, you have to make some creative fixes here, if it's possible. If we want to reconstruct global topology and not just geometry, we really only need to know certain important distances, which are distances between points in adjacent Voronoi cells, at least if we're working with not the full skeleton. So can we get improved bounds in this setting? And lastly, how can we best use the distribution of persistence diagrams as a feature in machine learning? In general, and especially in this case where it's quite structured, we know that all of our diagrams come from subsets of a bounded size of a given space. So actually there's a number of different ways you could try to do this, and we're working on this right now. But the question is, which one works best? And when I say works best, I mean, first of all, it ought to work on some data and also have some nice theoretical properties. So that's what we're thinking about. So let me give you some highlights. Distributed persistence is bilipschitz equivalent to the quasi-isometry metric. The Lipschitz constant is quadratic in the size of subsets. Even for sure for the RIPs in general, whether you're working in any metric space, and the check, which only really works in Euclidean space, you can also get such a quadratic bound because of the interleaving between RIPs and check. You don't need to check that many subsets. With a little geometric data, the bound becomes linear. And you can check even fewer subsets if you start relaxing what kind of metric you want to be working with. Optimization using the invariant can quickly overcome sort of large initial noise, as in those examples. And it's easy to compute, and it has many applications. It's a pretty flexible invariant in the sense that persistence is flexible. So that's the end of the talk. And I just want to say that, so someone recommended this. I'm going to try to adopt this practice. So that's my name and contact information there. And outside of this talk, I'm always happy to discuss and collaborate and talk more about this project and other projects.
All right, let's go ahead and give Elchanan a round of applause, and then we can go into questions. So. All right, I'm also going to stop recording.